Jeezo peezo, Moser. Okay, this is 12, 16, 14. So we're doing Gooch method for nitrogen. N2. First, we are figuring out the valence electrons. Second, we are counting up the octet electrons. Now, our third step, we want to know how many electrons they're going to have to share. Well, if they want, between them all, they want 16, but they only have 10, how many are they sharing? They're sharing 6 electrons. Okay, they are sharing 6 electrons. Now, step 4, how many bonds are there? Well, every bond represents how many electrons? 2. 2, and 2 shall be the number. So, 6 shared electrons divided by 2 gives us 3 bonds. Now we only have one more step. We need to figure out how many unshared electrons there are. So, step 5. There are 10 valence electrons that we started off with, and we're sharing 6 electrons. How many unshared pairs are there? There are 4 electrons that are not shared, so 2 unshared pairs, right. Make sense? Seem good so far? Okay. Now, let's draw this puppy. Let me shrink this. Okay, so we have 2 nitrogens. How many places can we stick 3 bonds here? I don't see a whole lot of options. 1, 2, 3, triple bond. Just 'cause I can. You can too. You can't do it during a test because you would alert others to the presence of a triple bond. But when you're doing homework by yourself at home, at Tim Hortons, at the library, wherever, if you want to go triple bond, I would encourage it. I think it adds an element of unpredictability to chemistry. Okay, so we've got a triple bond. Are we done? What do we have left? 4 unshared electrons, so 2 unshared pairs. So boop, 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 boop. Are we done? Hey, lo and behold, we are. And this is actually the form that nitrogen appears in the wild, as it were. Out in the environment, the wild nitrogen that's circulating in the air right around you, right now, we are surrounded by wild nitrogen, is in this form. It's diatomic nitrogen molecules, and they're triple bonded to one another with an unshared pair on each end. So they line up like a little straight line of nitrogens. On a scale of 0 to 5, 0, I'm not sure what electrons are. Who are you? Why am I here? 5, psh, I got this. I can do anything you want me to. Bring it. Where are you? Fingers. Okay. Lots of 3s and 4s. That's where I want. That's what I want to see. 3s, and 3s are fine. And if you're feeling like you're a 2 and you want to give me the sneaky 2, that's okay. We'll be working with this extensively. Oh yes, lots of fun. Okay, so these are all pretty easy in terms of when they're not charged. Do you sense what's coming? Charged things. Okay, so let's talk briefly about polyatomic ions, shall we? Okay, so we're gonna skip up a little bit because I want to talk. The book does not handle it in this order, which is why the slides are in the order they're in. But I want to talk a little bit about polyatomic ions and what they are. So you know what an ion is. A monoatomic ion is what? one atom that's either gained or given up electrons. Great, it's got a charge. Well, here's the weird bit. We can have groups of atoms that are covalently bound together, so we think group of atoms covalently bound together. It's a molecule! But part of the definition of molecule is that they are neutral. So if we have something that is covalently bound, they're sharing electrons, and then that group of things collectively either gives up or gains an electron, we now have what's called a polyatomic ion. This is not rocket science. Poly, more than one. Atomic, more than one atom. Ion, it's an ion made up of more than one atom. So sulfate is a great example, and we'll go ahead. Actually, you know what? Let's start off with a hydroxide. So hydroxide, you will use this a lot. OH, and it has a 1- charge. Okay? It's one of the most common polyatomic ions. You'll use this extensively. When we get into the next chapter, one of the first things I will give you is what I fondly call the Ion Bible. It is the be-all and end-all for polyatomic ions and common ions, and you will get really, really, really good at using it, and you'll have like 7 copies of that crammed in different parts of your books and your life and your locker and your car and whatever else. These are something that you can't do chemistry without understanding. So what we have here is an oxygen and a hydrogen. Let's imagine how that, so forgetting for a moment, let's just for a moment forget that. Only for a moment, we're going to come right back to it. If you just, without Gooch method or anything, had to line up an oxygen and a hydrogen, how do you think it would look? Go. There's an oxygen, there's a hydrogen. How could you hook those two things together? This is not a trick. It's just a thought process. Okay. James. Okay, so something like that. Okay. We have one problem. What is that problem? We have a lone electron there. So there are a lot of things that could happen. We could find another hydrogen. But very often what happens is that in common substances, and I'm going to color code this. I apologize in advance. This may not be as clear to all of you as it is to some of you, sorry. Yeah. Can you see that? That's a bad color combination. Hold on. This OH picks up an electron from someplace out in the world. Are there free electrons roaming the world? You bet. They're all over the place. You ever get zapped by a doorknob? It's free electrons roaming the world. You know, either jumping off of you or jumping onto you. Either way, it goes beep. So this OH picks up an extra electron. Well, if you've got an extra electron, now you have a charge. What's the charge on this group? -1. It's got one more electron than it does protons. So that's, I mean, really, it's that simple. That's a polyatomic ion. Clarity? Seem clear? Group of stuff that was already sharing, and then they pick up a stray electron, or they give up an electron to even things out. Let's do another example. We'll do sulfate, because that one's pretty straightforward. And we're going to then walk into the Gooch method. So SO4, whoops, 2-. SO4 2-. Okay, so we know, now if you look on the back of your Gooch method sheets, Goochity. Step 1 for this is the same. Step 1 starts out the same anyway. So we want our valence electrons. So sulfur has how many? 6. And we only have 1 sulfur. Oxygen has how many? 6. And we have 4 of those. But here's where it diverges a bit. If you have a charged group, if you have a polyatomic ion, you now have to either add or subtract electrons based on the charge. So this has got a 2 minus charge. Does it have 2 extra electrons, or is it missing 2 electrons? 2 extra electrons. So we got 6, we got 24, and we have plus 2 electrons. So that gives us 32 valence electrons. Okay, I'll move that up. Okay, step 2. Nothing different in step 2. Figure out how many electrons everything here wants. So, sulfur wants 8. We only have 1 sulfur. Oxygen wants 8. We have 4 oxygens, so we get 8 and 32, or 40. Octet electrons. 40 octet electrons. Okay, step 3 is the same. We want 40, but we have 32. How many of these are we sharing? 8. Okay, and step 4, of course, how many bonds does that represent? 4 bonds. Okay, now what's our last step? Unshared pairs. So and let me shrink all this. So step 5, we want to find our unshared pairs. If we have 32 and we are sharing 8, we have a whopping 24 unshared electrons, which means 12 pairs of unshared electrons. Okay, so which of these things is going to be in the middle? Intuitively, sulfur. Right. Remember, if we've got 1 of something and 3 of something, it's probably the 1 of something that goes in the middle. If you've got carbon, what goes in the middle? Carbon. Other than that, it's the thing that's least electronegative. Okay, so let's put our sulfur in the middle. How many bonds do we have? 4, really. 1, 2, 3, 4. Well, that was nice. I kind of like that. How many unshared pairs? 12. Does sulfur have any room for unshared pairs? Guess where they're all going? Out on the oxygens. 3 on each. Now, because this is an ion, and there was something I made a mistake about yesterday I have to correct with you, but because this is an ion, we have to enclose it in brackets, and we have to show its charge. Okay? we have to show its charge. You don't have to do brackets for resonance structures. You only have to do brackets for resonance structures if they are ions. And I made that error yesterday. So, okay. Level of comfort with doing these for polyatomic ions. Do you want to do one more together? Okay. Well, let's do that example where we have resonance structures and polyatomic ions, shall we? Let's mix it all in a one big pot and stir. We're going to find the valence electrons. We have nitrogen and oxygen. How many? We'll try to do this as quietly as possible in deference to those who are walking through it on their own. Hold up fingers. How many valence electrons does nitrogen have? Okay. And oxygen. And that's times 1, that's times 3. And do we have extras or fewer electrons? Plus, right. So we've got that. You're all coming up with the same thing? Okay. Step 2, octet. Step 3, shared. Step 4, and step 5. How many unshared pairs do we have? Okay, so at this point I think we are ready to start some drawing. Oops. Okay, we figured out that nitrogen's in the middle because we've only got one nitrogen. Now we have how many bonds? Hold up fingers, those of you who are doing it with me. Okay. Well, let's see. 1, 2, 3. What's going to happen here? Double bond!
But which one?
Unshared pairs? Unshared pairs? Going once, going twice? 8. 8. 1, 2, 3, 4, 5, 6. 1, 2, 4, 5, 6. 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. Well, there it is. Are we done?
Does it matter if the double bonds on that side?
Ah, that's the question. We're not done. All 3 ways. So, first we got to bracket this puppy, and this is 1 minus. Well, then we're going to have to take this over to the next page because we got some writing to do. And I'm going to shrink this. Okay, so now we have that arrangement. Well, how do we know that the double bond isn't down there? how do we know? And typically this is considered bad form. I'm only doing this because I don't have space. That is some pretty ferocious wind out there. Rain and wind. Okay, so for the nitrate ion, if you don't write all three possible locations, it's wrong. You have to show the resonance for that. And you have to show the brackets because it's an ion, and you have to show the charge. Question. So when you've only got one double bond, how do you distribute your unshared pairs? The unshared pairs are, you're going to have one fewer. This is that octet check that we need to do. So let's do our quick little octet check. For this nitrogen, how many electrons does it feel like it's got? 2, 4, 6, 8. Is it happy? Yes. For this oxygen over here, this way, 2, 4, 6, 8. Is that oxygen happy? Yes. 2, 4, 6, 8. Is that oxygen happy? Yes. 2, 4, 6, 8. Is that oxygen happy? Yes. So that's the process of octet check. And yeah, if you've got a double bond someplace, it's going to replace very often an unshared pair. Yes, ma'am?
So when you have a hydrogen, what is octet number 2?
Hydrogen's octet number is 2. Hydrogen doesn't go for an octet. It goes for a duet. So if you're in music, you can think about that. Hydrogen sings little duets with itself and other things. Okay, questions, comments, concerns? You want to just work and I'll float? We'll call it there.